All right. Mic should be on. Yep. We're reading. Hey, Matt, you hear us okay?
Yep. Yeah, I can hear you.
The camera's right here.
Something's blocking something. Oh, the projector. Would you rather sit on this side?
I was trying to see if I could, because I want to.
Yeah, you're welcome to sit here if you want.
Yeah.
I'll just move this over.
With this thing.
Oh, this is really blurry.
Oh yeah. Oh, this is autofocus, but you can do manual focus in case you have that.
It's already maxed out on the autofocus.
Oh, then dial it back.
We need people to look into the Google Hangout. Backlight compensation as well.
Let me know when
You're good to go?
Oh, yeah.
All right.
Good to go.
Ladies and gentlemen, thank you. Welcome to Toronto Permalunkers March of the Makers. First up, we have Jeff Razon.
Hi. Thanks. So hi, my name is Jeff. I'm a graphic designer. I wanted to thank everybody for taking their time to listen to what I have to say. I wanted to tell you a story of my mini adventure into the world of Internet of Things, or what everyone else calls it, IoT. A few months ago, I attended a conference called FITC. For anyone who hasn't gone yet, I highly recommend it. It's definitely an experience worth saving for. Anyway, there were a bunch of vendors set up at the event. One of the stands, called Influxes, were giving away Arduino boards. If you signed up for their beta account, they just handed one over to you. Obviously, being a fiend for free stuff, I signed up. I'll be honest here, I knew nothing about Arduino, nothing about coding a sketch, and had no clue what people use them for. Anyone's worst guess would have been smarter than any of my guesses. Naturally, I did what any logical person would do with a situation like this. I put it away, out of my sight and out of my life. A few days had gone by, and some of my thoughts trickled into my head. I started getting curious about what the heck that thing in my Tupperware was. So again, I did what any logical person would do in a situation like this. I played my favorite video game for hours. Then, I actually Googled it. It turns out, this little thing was actually capable of a lot of things. I went through hours of video, and I learned how to make an LED blink. In fact, I probably learned it like 5 times in English and what I think could have been French, so I learned it a lot. People from around the world in various age groups, from kids to adults, were making use of this thing. They made simple fans up to something crazy like a self-maintaining garden with sensors that help moderate temperature and moisture. Again, I did what any logical person would have done after hours of research. I started playing around with Arduino. I made it blink. I made it blink a lot. Actually, I made it blink many times. At this point, I felt so powerful. I was like, yo, I could do anything. I knew it wouldn't be long before I would be able to build these for myself. Yeah. So I began planning for my next project. I was still learning, so I knew I had to start small. So I decided to make a 3-axis gimbal. It's a camera handle, and like its name suggests, it rotates along 3 axes. What it does is it stabilizes camera movement, which allows you to film super smooth footage. The image you're seeing is a version made by a company called DJI. It retails for about $2,500. If I were to make something like this on my own, I estimated that the price would be just shy of $1,000. It wasn't hard to break down the whole structure. With a bit of research, I just needed a few pipes, a few brushless motors, an accelerometer, a gyroscope, and a few wires, and voila, I would have my 3-axis gimbal. This section is called wilting. This is how my project looked like when I started. Like any plant, if you had an idea without sufficient amount of care and attention, that idea will die. And boy, oh boy, learning new things is time-consuming. Yes, it's true. Oh, sorry. This is actually how it looks like now. Yes, it's true. This is a sad story. However, the moral of the story was never about success or awesome things or plans. I tell you this story because up until this project, I was always afraid of failure. I would have rather just bought the ready-made product, and let's face it, it's way easier. But is that really an example worth setting for myself in the future? The answer is no. What I learned, truth be told, it was never really a failure, just another seed waiting to be watered. Before I started this project, I had no clue what Arduino was, but now I have the skills to make something that interacts with the world. I know what a sketch is. I learned so many things that people were doing with Arduino. Whether I follow through with the project or not does not stop me from coming up with awesome ideas, nor will I stop from pursuing new ideas. My message to you, if you're curious about exploring new things like Arduino or Raspberry Pi, then get your hands dirty. It gets frustrating at times, but at the same time, you could find yourself really enjoying the learning process. And remember, it's okay to fail. You always have more seeds. So thanks for listening. I'd like to thank Dave for allowing me to speak today, and enjoy the rest of the presentation.
Did you find any good sources of information on the application?
Yeah, so I did a lot of researching. I found I have the accelerometer, and I found out how to actually get it to work. The issue was that because the accelerometer was like from a Chinese maker, it was hard to kind of figure out how each of the axes works and all the information it was feeding back. At the same time, I have 3 motors, and I was actually missing another part, which was the controller for the motor that allowed it to either spin one way or another way, and the amount of power input that went into it. I didn't want to get into the details of that stuff because I mean it's really ugly and slow, so I just avoided that. But I'll get there eventually.
I'm thinking more of the learning process, or any books or sites that you found especially helpful.
So a lot of there's a lot of information on the actual Arduino site. They actually break down chips and various parts of like how to control a chip and the maker and all that. But also like a really good source for me was YouTube, even though probably like 90% of it is kind of crap, but sometimes you'll get some really good information on there. Yeah. Thanks.
Thanks so much, Jeff.
Thanks.
And next we have Avianna Chao talking about her adventures in 3D printing.
Hi everyone, my name is Avianna, and I'm here to talk to you about 3D printing. Also what I like to call how to get all the beep out of your head and into reality. So 3D printing has really come into the mainstream these days. I hear that even Canadian Tire sells 3D printers now. I haven't gone there to check it out myself. Anyway, the first time you probably heard about 3D printers, you probably thought it might work something like Star Trek replicator technology. Where you walk up to it and you might ask it Earl Grey hot, and you'd be presented with a really nice hot cup of tea. Anyway, so tonight hopefully I will give you a good overview of 3D printing technologies and how they work and how they differ, and talk about a little bit about the materials that 3D printers use, and where to get the 3D models that you might want to print, and also some of the challenges you may face. And then we'll talk a little bit about where I think sort of the new and interesting things that are coming up in the industry. And hopefully by the end of the night, you'll have a better idea of how to answer whether or not you can order some Earl Grey from a 3D printer. Okay, so there are three main 3D printing technologies. Like first one is called SLA, or stereo lithography. Don't worry about the details. Like I will go into these in more detail and explaining how each of these technologies work. So the next one is SLS, or selective laser sintering. And then the most popular one is called FDM, or FFF. Now FDM stands for Fuse Deposition Modeling. This is actually a trademark term by 3D printing giant Stratasys. So because they trademarked it, we can't really use it. So we generally, in the open source community, we talk about fuse fabrication, fuse filament fabrication, or FFF. Now all of these are additive manufacturing techniques. So additive manufacturing is basically saying that it's different from traditional like CNC manufacturing, where you're starting with the block of material, and then you're removing parts of the material that you don't want, and you end up with the object. So additive is like the opposite, where you're essentially adding layers on top of another until you get the 3D object that you want. This is actually not a new technology. It's been used in many industries for many years. But just in recent years, the prices have come down because I think certain patents expired, and so that's why allowed sort of this new industry to show up. So SLA is one of the technologies. It's stereo lithography, and so how this works is basically you start with a tub of resin, so a tub of liquid, and then this resin is hardened by shining UV light on it. So, so you have a tub of resin, and something projects an image of a layer of the object you want to print. That slice of the object hardens onto the print bed, and then the print bed is lifted a little bit, and then the next layer is projected on, and then so it keeps doing this until it looks like you're essentially pulling a solid object out of a tub of liquid. So it's kind of neat. One of the really cool parts about this technology is that, so even though I described it as it's a step-by-step thing, it's somewhat of a continuous process. And so because of that, the z-axis of the objects that you get are incredibly smooth. You don't get very distinct line breaks between the layers. And also because each layer is made by shining a light pattern onto the bed or the resin, you have very fine X and Y detail, right? So you end up with an object that is incredibly smooth in all the dimensions. So that's the really cool thing about this technology. The downside is it's rather expensive. So the printer that I've shown here is from a company called Form Labs, and this printer is I think about $3,300 US. And then so that's once you get the printer, that's great, but you also need the materials to work with, and the materials are also pretty expensive. I think for a single liter bottle of this resin, it's about $150 US. And also because you're starting with resin, which is essentially like it's colorless, you're limited to the number of colors. So the company also sell you like various dyes, colors that you can mix into the resin to make the colors you want. Anyway, so it produces really nice prints, but very expensive. So now we talk about selective laser sintering. So this is somewhat of a more traditional 3D manufacturing technology. It's what the like large engineering companies have been using for a long time now. To make small batch runs of things, or making molds for casts and so on. So how this works is that you actually the consumable here is actually powder. So you can get like plastic powder, or you can even get metal powder. And so you have the print bed, you have the laser, that high-powered laser, which melts the powder, and that creates one layer of the object. And then the print bed is lowered a little bit, and you have a powder drum, and then it pushes another fresh layer of powder on top of what you just printed or what you just sintered, and then you have a next layer, and then the laser does the next layer, and so it keeps doing this fresh powder to allow the laser to make the next layer, and it keeps dropping, and that's how this printing method works. one of the really cool things about this sort of 3D printing is that because essentially you're always pulling the object down and you're always putting more powder on top, by the end of the print, your entire object is essentially sitting in a bath of powder. And because of that, you don't need ever to have any support materials. And we'll talk a little bit more about support materials later on. But because you don't need to have any supports, it actually makes printing some really tricky geometries very easy. So that's one of the upsides. Obviously, if you use metal powder, you can make metal objects, which is really not possible with any of the other two technologies that we talk about. The downside is that these things are rather large. They're like sort of the size of your large, bedroom closet organizer. And also, it's kind of expensive. They're like probably starting around $100,000. I did see one on Kijiji for about $147,000. I'm not sure why the person put it on Kijiji, because I don't think if you're looking to spend $147,000 on a 3D printer, you really go to Kijiji as your source. But that's just me. Okay. Anyway, so the most popular form, the most popular technology used in sort of home office 3D printing is FDM or FFF, fused filament fabrication. And this is sort of the basis for the RepRap movement. You may have heard about that. Now, RepRap stands for Replicating Rapid Prototype. So the reason it's called that is because a lot of the kits or even the pre-assembled RepRap machines that you can buy, a lot of the non-metal parts are made from plastic, that are made from 3D printed parts. Right? So you say you get your printer all up and working, you can actually make replacement part, because say your 3D printed part, I mean, it might break someday, right? So that's the replicating part of it, right? And you can also improve upon the existing design. So the other people could also improve on it. So and that's the rapid prototyping part. You can drop a design in a CAD program and then print it out and then install it on your own printer, see if it works, and maybe improve on it. So that's the rapid prototyping part. So that's the RepRap movement. So how does this technology work? Well, it's actually very simple. Right? So you have a thermoplastic filament. So it's really just like a thin noodle of plastic. And that's pushed into a hot nozzle, generally somewhere around 200 to 250 degrees Celsius. And so when you push it into the hot nozzle, the filament melts, becomes a liquid plastic, and then that plastic is deposited on a build platform of some sort. And the platform may be heated or maybe not. If it's heated, it helps the hot plastic stick to it better. And if it's not heated, then you have to do a whole different number of tricks to make it stick, because otherwise the hot plastic doesn't want to stick to something that's cold very well. So basically, you have the plastic, hot plastic, it's deposited on the print bed, and then the print platform is lowered a little bit, and then you draw the next layer, and you just keep doing this until you have your fully formed object. Now, you can get a reasonable quality FFF printer for about $1,000. Now, obviously, there are more expensive consumer-level FFF printers out there, but about $1,000, you can get a pretty decent one. One of the other really good things about this technology is the cost of the consumables. So the filament, the plastic that you're going to be making your prints out of, it's fairly inexpensive. And there are a lot of different materials out there, different colors and so on. Again, we'll talk more about that later on. Okay, so we're going to just go through a little bit about the details, components of an FFF printer. So first thing you need is you need a frame, right? So that's this entire thing that it sits in. Now the frame can be made. I've seen printers made out of wood or acrylic or aluminum or even stainless steel, right? Ideally, you want to have as rigid of a frame as possible, because everything inside of the printer is going to be bouncing around. It's going to be moving around, right? So I don't know if you remember the old days where you had an inkjet printer. And if you had a not as stable, like a wobbly desk, and the inkjet is going slam, slam, slam back and forth, the entire desk shakes, right? So you don't want that, because if the entire frame is shaking, then you're going to lose a lot of quality on your final print. So you want a rigid frame, and then we talked already about the filament they come in rolls of plastic, so it comes in a spool, and then so the filament gets fed into, here's the actual extruder, which contains a heater block, and then the actual very small nozzle. So essentially, plastic goes in, gets heated, melts, and comes out, and is deposited on the print platform, the bed. And in this particular case, the extruder moves X and in the X and Y direction, and then the bed is moving up and down in the Z direction. Okay, a little bit more about how the actual extruder works. So this white drawing part here, think of this is the actual motor. So you're looking at it face on. So this is the extruder gear, the drive gear. Right? So this is spinning clockwise. And this is the filament here. This is just a bearing that helps to keep pressure on the filament. So the extruder gear is essentially grinding, it's pushing this filament straight down into the hot end. And the hot end is this part here. So you have a heater cartridge and then a thermometer. And these two things are connected to your main controller board. And this actually system is very simple. It's just a feedback loop. Basically, you set the printer to a certain temperature, and basically the controller goes, what's the temperature? And if it's below the temperature that you set it at, it applies voltage to the heating element. Thing heats up, temperature sensor reads, goes back to the controller. So you have this feedback loop. And then so basically, you're constantly feeding more and more filament in here, it gets melted into liquid plastic, and it gets ejected out of this small nozzle at the bottom. The nozzles can come in a variety of sizes. Probably the most popular one is a 0.4 millimeter nozzle, so it's a very small hole. And because you're constantly pushing more filament in, the melted plastic really has nowhere to go but out the nozzle. And so this is one of the reasons, one of the misconceptions of FFF technology is that it's gravity dependent. It's not. Because you're constantly applying pressure by injecting more plastic into the hot end, this really has nowhere to go but out. And so it doesn't really matter if this entire setup is pointing upwards and gravity is pulling down or it's pointing sideways. It really doesn't matter. The hot plastic is going to come out one way or another. Right? And you may have heard that NASA famously, they sent up a 3D printer to the International Space Station. And they did some tests, and also one of the tests is that they wanted a wrench, and instead of waiting for the next resupply ship, they just sent up the design file for the wrench, and they printed it in space. And it was certainly a lot quicker, and also probably a lot cheaper than waiting for the next resupply ship, which may or may not blow up on on the launch pad. For those people who are here, I do have a printed copy of the wrench. Unfortunately, I kind of broke this, so it doesn't ratchet anymore. But it did print very well. I did print it out of the wrong plastic. I should have printed it out of ABS, but I printed it out of a different material. Anyway, you can have a look at it later on.
Stick it in front of the camera if you like.
That visible?
A little bit, yeah.
That's the projector. Yeah, it's not the camera.
Anyway.
Camera's on the computer.
Okay, anyway.
No,
That's the camera. No, it came on.
Okay. All right. Now, so there are a large variety of FFF printer setups. Just showing two of them here. The one on the left here, this is a board-bought quantum printer. This is a do-it-yourself kit. You buy this kit and you assemble it yourself. It's one of the nicest looking kits that I've seen. So, for example, in this particular setup, the bed here, this glass bed, is moving in the y-axis. It does not move in the z-axis. But you see, here's the filament, right? So here's the extruder part. So it's going to push the filament down. So the extruder here has a motor. So this motor moves the extruder left and right, or along the x-axis. The bed is moving along the y-axis, and then these two motors here, they move the entire carriage up and down the z-axis. So this is one particular setup of a FFF printer. The picture on the right, this is a craft bot from Craft Unique. this is my printer. Well, not this exact printer. I have the same printer, but a different color. But this one, for example, the bed here, you see, is riding along these rails. So this is the z-axis. So the bed moves up and down. And then here's the extruder part. And this moves along the x and y-axis. So there are different setups for these FFF-type printers. And they each have their own benefits and problems. And it really depends on what you're trying to do. One of the really interesting setups for FFF printers is something called a delta configuration. So instead of having a rectangular setup or a square setup, you have this delta shape, and you have 3 main rods, and you have 3 motors that move, can move up and down along these rods, and they're connected to the extruder via fixed length rods. And so now imagine that by moving these motors independently around, you can essentially move the extruder anywhere along this build platform, right? So this is one of the interesting setups, and because of the nature of the setup, these Delta printers, they're very good at printing things that are, somewhat circular in shape, like statues or vases and so on. And also, one of the obviously identified marks of this configuration is the circular build plate, or sometimes you get a triangular build plate, whatever that fits into this setup, right? They tend to have limited X and Y capabilities, but they have a much larger Z capability, so you can print things that are long and tall. Okay, so let's talk a little bit about the actual materials that you print with. So PLA, or polylactic acid, and ABS are the most popular materials. I'm not even going to try to pronounce like the actual name for ABS, it's crazy long. They're the most popular because PLA is actually made from corn, and it's biodegradable and etc. And so it's actually very friendly to the home office environment. It doesn't smell like burning plastic when you're printing. Actually, it doesn't smell like anything, right? Whereas ABS, it literally, if you print ABS at home, it smells like burning plastic. So you want to exhaust those fumes outside. You don't want to be breathing in melted ABS. So because of that, sort of PLA wins out. And then you have more interesting materials like nylon, which gives you different strength properties. Or you can have a sort of a rubbery material called TPE, thermoplastic elastomer. That's what this iPhone case is made out of. Now, it's kind of a weird thing to be printing a rubber iPhone case with your 3D printer, considering it's going to cost you like $1,000 of investment, whereas you can probably buy the iPhone case from Chinatown for like $5. Anyway, so some of the other interesting materials you can have are actually dissolvable materials. So remember, I mentioned quickly about supports that you might need to have in your models. So how do you make the supports? You can make the supports out of just the regular PLA or ABS. But the problem with that is when you finish, you gotta remove those materials from the print, either with an X-Acto knife or file or whatever. And sometimes it could be a real pain to get it removed from your model. But if you print the supports out of this dissolvable material, then you can just take your entire model when you're done, stick it in the thing that dissolves the supports, and then pull it out sometime later, and voila, your model is clean and beautiful. So that's why you might want to have dissolvable materials. Now, some of the more interesting materials that's come out in recent years is PLA that's actually infused with other materials like wood, stainless steel, carbon fiber, or even copper and bronze. So like this elephant here, this is printed with a wood fill. So it's 40% wood and 60% plastic. Because of that, it actually inherits some of the properties of wood. So when you finish printing, you can actually sand it, you can drill it, you can do whatever it is that you normally would do with something made out of wood. So that's pretty neat. Now, the really interesting ones are the conductive PLAs, like the copper and bronze. Not only are they good at making little figurines here, now, okay, they don't actually come out of the printer quite looking this good. They kind of come out a little bit, rough. So these figurines are shown here that are there's a lot of post-processing that being done with it. So a lot of sanding, a lot of polishing with polishing compound and a steel wool or steel brush. But at the point is that you can make really metallic-looking objects from your 3D printer. Now, of course, it's nice to make figurines, but the really interesting thing to makers is to be able to print essentially a circuit with your 3D printer, and you can definitely do that with conductive PLAs. And I think there's some models out there that allow you to print the circuit in place, and then when it's all done, you just pop in a battery, and boom, you have a working actual thing, working electronics project. It's pretty cool. Okay, so where do you actually get the 3D models that you want to be printing? And what form did they come in? They come in something called a STL file. STL officially stands for stereolithography. It's the standard file format for exchanging 3D printing files. But actually, it's probably better, a better acronym or a better explanation of it is a standard triangle language. And the reason for that is, so your 3D modeling program might show you a nice, smooth, and beautiful 3D model, but actually, if it saves it as an STL file, it turns them all the entire 3D model into essentially a large array of triangles, and that's sort of what your 3D printer is going to consume. I will put an asterisk on that comment because that's not technically correct. I will explain later on, but let's for now just pretend that's the way it works. Okay. Anyway, so the largest free and public resource for 3D printable models is something called Thingiverse. It's a website made by MakerBot. That's one of the 3D printer manufacturers. They do make some of the nicest looking 3D printers out there for the home office space. But because they look so nice, I think, they also cost a lot of money, and I haven't had the privilege of playing with any of them, so I don't know how good they are actually at printing things, but they certainly look awesome. Anyway, Thingiverse offers you a massive collection of 3D printable objects, and it's all free to download. And one of the really neat things about Thingiverse is that there's a huge community of designers and makers that are constantly putting out new models to print that you can just download and print. And one of the really useful features is that once you download a file and you print it, you can actually take a picture of it, of your print, upload it to Thingiverse so that when someone else comes upon this object page, they can see that, oh, maybe like 15 people have made this print and succeeded, so maybe they'd give it a try as well. So it's a really nice community, and so Thingiverse is where it's at for getting free models. I mean, there are other ones out there, but this is sort of by far the best one. Now, what kind of a maker are you if you don't want to design your own model, right? Now, so I don't know if you had ever had the experience of working with AutoCAD. I did that growing up, going through high school and to learn drafting and work with AutoCAD, and it was like super unfriendly to use. Well, so I actually started to do my 3D modeling not in AutoCAD but in something called Tinkercad. It's a web-based 3D modeling setup. It's super easy to learn, and they've done something really powerful. They give you basic geometry shapes, and then you can do Boolean operations on them. And you can really be surprised what you can do with just basic geometries and Boolean operations. And the whole thing is browser-based, so there's nothing to download or install, and it runs on any platform that you have a good browser on. And it's just super easy to use. Now, the funny thing is, Tinkercad now is actually owned by Autodesk. And Autodesk actually has their own free-to-download and run 3D modeling program called 123 Design. But I would highly avoid that. Like, it's terrible. They've tried to copy things from Tinkercad, but they've just failed. It's not good at all. I've also heard good things about Google SketchUp. I haven't had a chance to try it out myself. Anyway, Tinkercad, I've had awesome success with it. Okay, so you have your 3D model that you've designed, but it's a 3D object, right? And so how do you get it to something your printer can understand? So remember the asterisks I talked about. The 3D printers actually don't understand STL files directly. It's because if you think about how a 3D printer works, it's it's drawing with liquid plastic. That's what it's doing, right? So it wants to have instructions that make sense to essentially something that draws a line. So this is where you need something called a slicer to turn a 3D object, right? A 3D object into essentially an array of two-dimensional slices, right? And then once you have a slice, one layer of the 3D object, then the slicer also turns that two-dimensional slice into essentially a path that the 3D printer can then follow and essentially extrude out the hot plastic, and that's how you make a layer. And you just repeat that until you have your entire model. So the input to a slicer is a STL file, that's your 3D model. And the output is something called a G-code file. And G-code, it's just a text file, basically. It's one instruction per line. And you can load a G-code file up in the text editor and look at it, and it's very easy to read. It contains a whole bunch of instructions that says something like, go to X and Y coordinate this, extrude this amount of plastic. And then the next line, go to this X and Y coordinate and extrude this amount of plastic. It's basically just that, but like 100,000 times.
Like a logo program.
Yeah. And then the printer reads the G-code and then executes it line by line. Right? Now, advanced users, you can actually edit your G-code directly and then maybe get access to certain features that your printer supports, but the slicer doesn't. A little bit more about slicers. So there are some open source slicers. Probably the best one out there is something called Slip3R. It has really extensive options to allow you to customize essentially every part of the printing process. And it also has something that's very important if you're actually printing objects that are mechanical in nature. In other words, you're not just printing a figurine where you really don't probably care too much about the dimensional accuracy. But if you're printing a mechanical part, it has to either fit into something or something has to fit into it. So it has to be dimensionally accurate. And Slip3R are pretty good at that. Now, the company that I have my 3D printer from is called Craft Unique, and they put out a program called Craftware as their slicer. And one of the really cool things about Craftware is that it has a really good visualizer for G-code. Now, why would you want to even visualize the G-code? Well, sometimes a slicer, so you start with a 3D model, you slice it, but what the output of the G-code may not actually be the same as what actually the model described. Maybe you have screw holes, but after you slice it, those holes get covered up for God knows what reason. So it's kind of important to examine the G-code, to visualize it in a visualizer, like Craftware, to see if there are any problems, because you don't want to waste the time of sending the entire print to your printer only to find out there's a problem in the code. There are commercial slicers also available. One of the best ones out there is called Simplify 3D. They've done a really good job at preloading the program with a huge number of printers that they support with preloaded settings that will basically out of the box give you fairly decent prints. So open source or free to the other programs, Slip3R and Craftware, they have like literally pages upon pages of options. And sometimes one of these options, can really change the quality of a print, and it's not explained very well. Well, Simplified 3D really did a good job simplifying this process so that you don't have to try to, find out what each one of the many, many, many options mean. And that's why you pay $149 US for it. Okay, so we talked a lot about 3D printing, but what can you actually make? So here I made a little Marvin, the Android model, with bunny ears. So Marvin is actually sort of the unofficial mascot of the RepRap movement. This is somebody's design, his stuck bunny ears on the Marvin model. This is one of the things that are available in Thingiverse. Actually have it here on the desk, you can look at it. And this is made out of wood, the wood-filled material that I talked about earlier. What else can you do? Well, you can print yourself some printer upgrades. So this is actually my printer. This yellow printer is mine. So by default, the spool of plastic is hanging on the back of the printer here. But when I got it, I wanted a second spool. And so I downloaded somebody's design from Thingiverse, printed it, and it works great. something else I printed from a design on Thingiverse. So this is my extruder, right? And these two are fans. So these two things, the fan ducts, did not come with the printer. Again, from Thingiverse, somebody designed it. Actually, this is a second generation of a design. There was the first generation that was sort of smooth along here. And then someone else saw that design, printed it, and decided that they could make an improvement on it. And then they made their own model, and this one really works very well. So this is the rapid prototyping part of RepRap movement. What else can you print? Well, you can print yourself some cable organizers, so that your USB cables aren't just sort of the ends aren't just dangling on the floor. Because these iPhone Lightning cables, they break all the time, and they're really expensive, right? You can print yourself a key holder so you don't lose your car keys or house keys. You can print yourself a private, ready-to-go, portable cloud storage system. That's pretty neat. And this thing here up in upper right, this is sort of this is my dishwasher here. I don't know if you can see it very well, but basically the dishwasher, when you have coffee mugs, when it finishes, there's a little puddle of water on top of the coffee mugs, and it doesn't dry it out very well. And so I used to just try to leave the door open a little bit so that it could just evaporate. But then, I didn't want to leave the door fully open because then the dust and stuff will get in and, make the dishes dirty. So I wanted something that just props open the door just a little bit. Right? So I took my digital calipers and measured this distance and this distance, and I drew this thing up in Tinkercad, and I printed it, and it works great. And other people have actually used it too, so I was rather happy to see that. It's up on Thingiverse. For makers, for electronic projects, this is one of my Arduino projects. I ended up having essentially 3 layers of boards stacked on top of the Arduino, and I just could not find an enclosure that would allow 3 stacked high. So basically, I just rubber banded it, and it always fell apart, or the rubber band broke, or whatever. It was terrible. 3D printer, make your own custom case. Done. Make custom cases for everything. Another one of my Arduino projects is a bit wider. Again, just drew it up on Tinkercad, printed it. Works great. This is a piezo sensor. This is an accelerometer. This is a force sensor. Now this sensor is particularly sensitive. It's very flexible and easy to damage. Again, I drew up these designs in Tinkercad, printed it, protect the sensors, and it works great. And it looks better too. It looks professional. And of course, you can print toys. Who doesn't like toys? You can print yourself a little airplane, which actually does fly. Maybe you fancy have your own personal Ed 209 from RoboCop. That's actually here on the table. It's a lot smaller than this picture might have you imagining. And of course, I had to dedicate an entire slide to my favorite print, the Blackbird. So both the Blackbird and the stand are 3D printed from my printer. The Blackbird is not my design. It's just something I downloaded from Thingiverse. And when I printed it, it was so nice, and I was like, I gotta display this somehow. So what am I gonna do? I gotta draw up a stand for it. So I did the stand up in Tinkercad, printed it, and then uploaded it back up to Thingiverse. I've gotten a lot of positive feedback about the stand. Anyway, so this whole thing is printed, 3D printed. Now, after all this, you might think, wow, things are really great. I'm just gonna run out there and buy myself a printer. Well, okay, hold on a little bit. I've only shown you the really good parts, right? There's a lot of trial and error. You can have errors in your design. Say you send a really long job to your printer, and then just before when it finishes, and you try to use it, and you realize, ah, crap, I'm like 2 millimeters off in this dimension, and it doesn't work. So error in design, big problem. You can have some error in your print settings. Remember the many pages of settings in Slick 3R or Craftware. If you mess one of those up, you could end up with something that's not usable. You can have problems with the printer. These printers, despite all the recent improvements, are actually fairly simple, right? It's essentially, these printers are like a couple of motors, a hot end with a thermistor heater loop, feedback loop to a controller, right? There's very little error handling, actually. Right? So something could go wrong with the printer that could ruin your print. Or you could have problems with the material. each one of the materials, and sometimes even different colors of the same PLA material, have different requirements in terms of temperature. If you get the temperature wrong, the print could be useless. The layers could not bond correctly, it could fall apart, or it could just be your temperature is too high and the thing just melts and it looks really terrible. So you can have problems with the material. So what you end up with is a bucket of failed prints that you really can't do anything with. Now this is not at all my entire bucket of failed prints. It's just a small sample of my failed prints. So probably don't just go out and buy the printer from Canadian Tire. Now to sort of wrap up, I wanted to talk a little bit about sort of the up-and-coming technologies in the 3D printing in this field. So most of the sort of affordable printers these days are single extruder. So you're printing with one material at a time. But now more and more, you're starting to see multi-extruder printers come out. So why would you want multiple extruders? Well, for one, you can print in different colors. Or more importantly, you can print in different materials. Remember the thing I talked about, the supports, right? If you have the dissolvable material in one extruder and your regular plastic material in the other extruder, then you can have essentially print the entire thing and then have the dissolvable supports. Because you really can't use the dissolvable support material unless you have a multi-extruder setup. You can also use conductive PLA, for example. So one extruder has the regular plastic and the other one has the conductive thing. Now you can print an entire circuit with a housing in one shot, which is really awesome. Right? Now, of course, multi-extruder printers have their own set of problems. So some people thought, well, we don't want those problems. We want to print multicolors or materials through a single extruder. So there's a Canadian company, actually, they kickstarted a project called the Palette. And what it does is it automates filament mixing. So this is what sort of this picture is showing here. So here on the left side, you can see there are 4 filaments going into their black box. They didn't show the black box here. And then out comes essentially a single strand of filament that you can hook into your single nozzle extruder printer. So all of a sudden, if you get one of these palette boxes, you've just seamlessly upgraded your single nozzle printer to be able to print multi-materials, which is really quite awesome. I do have a typo on the slide here. There's this company called E3D. They also made a somewhat simpler system. It's not called the Volcano. It's called the Cyclops. And what it's a single nozzle with multiple with multiple filament inputs, 2 inputs. So it will do automatic switching and mixing and so on. So again, multiple materials or colors through a single extruder. It's very cool. Sort of the holy grail of where we want to see these things go is the all-in-ones, right? So you can hopefully get a all-in-one 3D printer, 3D scanner, laser engraver, and CNC milling machine all in one. Because if you think about it, all of these technologies require the same sort of setup in terms of X, Y, and Z movement, but they just require different heads, right? A printer head, a scanner head, a laser head, or a mill. So that's sort of the holy grail, because once you have that, you can use the 3D scanner to bring physical objects into your digital world, do your editing or improvement, and then print it back out with your 3D printer. Maybe do some CNC milling for if you're working with circuits, pre-drilling holes or whatnot, and then even put your name on it with the laser engraver. So sort of that's where I would like to see this technology go. And you're starting to see some of these show up on crowdfunding sources now. Now the really important thing, the really big revolution I think about this 3D printing is about the changing of way of thinking. So in our society, it's very much we are consumers of what these companies put out, right? If we're not happy with it, or if something starts to not work, you just throw it away and buy a new one. But with 3D printing, it encourages people to think about, wait, maybe I can fix this thing. Or maybe I can just improve upon its design and make it work better. Or I have some completely new idea and I just want to take it from a 3D model and now I can make something completely from thin air. So I think that's the real big change that's been brought on by the RepRap movement and 3D printing. So really, it's all up to you. You know, go forth, design, tinker, create, and engage. And maybe one day you'll end up with some Earl Grey hot tea. I'm Avianna, and you know, if you have questions, hold on. I will show you one quick video of one of the things that I was printing. If I can start it. So this is a simple time lapse of my printer printing a flashlight holder. And so as you can see, this is actually, I think, like a 2-hour print. And so it looks really nice and fast here, but it takes its time to print. So now you see it's starting to print the screw holes, and then it's going to continue and move up. This is not a very big object. It's about 2 inches in size. And then it's done. And so that's how it sort of it looks. So yeah, so that's what I have. Hey.
How much does the filament material cost, and how big an object can you make out of a spool that you buy?
Right, so the filament is actually, the PLA and ABS materials are very affordable. One spool is going to cost you about $30, and that gives you about 300 meters of filament. And
kilogram.
Right, it's 1 kilogram, and based on the density of the plastic, it's about 300 meters. And so, for example, for the people here in the office, you can see I brought, and my friend Sergey has brought some show and tell items, and one of them is one of these racetrack things for marbles. And this thing is actually probably the longest print I've done, and I think it was like 18 hours or something like that, and about 50 meters of filament is in there. That gives you a sense of how much filament it takes to make something of reasonable size.
Material cost of that would be 50 meters?
50 meters out of $30, it's like 1/6, so like $5.
Do you know how much filament something's going to use to print it?
Yes, the slicer gives you a very good estimate because it has to do the entire pathing for the nozzle, right? So it knows exactly how much material is extruded. So it will tell you how much material you need. Now the downside is these filaments just come in spools of plastic, so there's no counter on it, right? So you kind of have to estimate, do I have enough in the remaining spool for this, 40-meter print? Because if you run out, yeah, you're going to end up with the bucket of failed prints.
And do you have any idea in advance how long the print was?
Yeah. So again, the slicer, it gives you some estimates. They're usually wrong, but generally for what I've seen, the estimates are usually off by like a factor of like 30%. So if it says it's going to be like, I don't know, 5 hours, it's probably going to be like 8 or 7 hours. So it's, yeah, it can take quite some time. So like I said, that thing about that size took about 20 hours to print. Right? So it's fairly normal to do something like this. Just let it run overnight. And as long as you don't have any material, like the spool doesn't get heated up, it should be good to go the following day or morning. Sergey actually has an interesting video of his print of the sub-zero mass, where you can actually see the sun go down, come up.
So does temperature or moisture ever affect the outcome of the prints?
Not so much for PLA, but for the wood material, I think they do recommend it. You keep it not too dry, because then it will become brittle, because it is 40% wood. You see that? That's the Ed 209. It's about 2 inches by 2 inches, and this took forever to print, and it took even more forever to clean out all the supports. Right? Essentially, this entire model was sitting in a plastic tub of supports that I had to very carefully remove, and I broke the leg in, I think, 3 places, and I had to glue it back together. So, yeah.
This is Sergey's sub-zero mass.
This is the sub-zero. which turned
Model
out
comes.
super awesome. You should put it on.
Oh, God. Really?
Abby, how often do you like design something and then it says this is impossible to print, it's possible to slice?
Right, so I didn't get into the details, the intricacies of designing for 3D printing. I think that's a whole different talk. There's a lot of things you have to watch out for. Really, you want to avoid support material at printing. If you can design to avoid it, you should do it because supports are just a pain. So there are all sorts of tricks and things you can do to design for not printing with supports. And then also because you're designing essentially something that's going to be bonded layer by layer, if you're printing something mechanical, you want essentially the bonding to be not, if you don't want to have the actual physical stresses be across those layers, because then you're testing the adhesion of the layers. So then in that case, you have to consider how is this object going to be used, and maybe you want to print it on a different orientation so that when the physical stresses act on it, that you're not going to crack the layer adhesion. Yeah, JP?
I didn't follow there, but unfortunately the thing that won't happen is it won't tell you, like the slicer won't tell you that it's impossible.
Oh, right.
What's going to happen is it's going to slice it happily,
Yeah.
and then you're going to get a pile of goo. Which is how you know it didn't work.
It sort of comes
When
with
the whole thing just
experience.
falls over and doesn't print. And eventually you get like, you figure out what's, like you get an idea of what your printer can do.
Yeah.
And you're like, okay, well that's impossible, I can't print this, I have to do something about it. But unfortunately the software doesn't really be like, no, I can't do that. It doesn't know that you can't do that.
There are also some limitations in terms of size. So very small things are challenging to print because again, you have this very hot nozzle and you're trying to print something and let it solidify and then you can print the next layer on top of it. So really small things, so anything that's like less than 2 millimeters is very hard to print. Whether it's a positive dimension, like an object, 2 millimeters in dimension, or a negative dimension, like a 2 millimeter hole, very, very hard to do, right? And also, to get it exactly 2 millimeters is very challenging.
But once you get like 1 millimeter or like 7 millimeter dimensions, that helps to clean up the print and try to like file it or do something with it.
My question was, sorry, follow up. Basically, none of these tools that you use are deterministic. What's possible, you have to know that yourself, basically.
Yeah.
Would that be like the next step in this technology is for it to analyze your model and say, you can't really do this?
Well, I feel like it's sort of true. Like the MakerBot guys are trying to do something that's more user-friendly, where you don't really need to know exactly how it works. You're just kind of like, oh, I want to print this. But it's still quite a ways away from that. Like, I mean, I'm really hoping one day we'll get to it, where it's like this where it just works.
The program would need to know what kind of printer you actually have, because they all have their own
Capability.
Yeah, well, and then it's kind of what happens when you first start with a slicer. You tell it what kind of printer you have. You like have a bunch of descriptions of what is it you have, but there's still differences. Like for example, I was showing with a direct fan on the nozzle, that changes what your printer can do. Whether you're directly cooling the plastic that's being deposited, that changes. So for example, you should be able to have more steep overhangs rather than drooping down, or like. But a printer that doesn't have that will have a hard time, right? Or another example is if some printers don't have a heated platform, like all the printers we're showing here, they have a heated platform on which you print. And what that does is allows like the prints to stick better to the platform. Because if you're at a cold bed, as soon as you deposit it, it cools down very rapidly. It basically contracts and peels off.
Yeah, too much light.
So when you're designing these things, like a really complex one, is it more about like composition, like in those regards, instead of having a printer do everything in one shot, you actually break it up into smaller pieces and then you bring them back together?
Yeah.
Ideally, like if you can avoid, like if you can print parts without support and then just put it together, that is better. Like for example, on Thingiverse you can go find this guy made a design for a full-size stormtrooper helmet.
Oh, nice.
So you can actually print like a whole thing and wear it on your head, but it is 24 pieces.
Right.
There's no way it would come out. Well, first of all, it's too big. That's the other thing that we haven't mentioned is that these 3 printers usually have fairly limited print volumes.
Right.
they're like yours is what 20 by 20 centimeters, 25 by 25.
25 by, yeah, something. Essentially 20 centimeters cubed.
Yeah.
And that is one of the larger print volume printers on a consumer home-based, printer. Some of them are much
10 by
smaller.
10. Yeah, there are lots of those 10 by 10. So like part of the limitation is that your print volume isn't big enough, and also it takes too long, and without supports, there's no way you can print this. So basically, this helmet is the 24 pieces that you then glue together, and then you have the helmet. So
Might be like silly, but have people even tried that one? Making a bigger printer?
Yes, there are massive size print. There's a printer at the.
No, like using the smaller printers to build components to build like a bigger printer.
That I don't know. But so one guy did make a. They just turned a regular printer upside down. Remember, I explained that this technology is not gravity dependent, right? So basically, he realized that the one of the things limiting the Z volume is that the Z-axis has to move down. And so eventually it's going to hit the bottom of the printer, right? Well, what if you flipped it upside down and the Z-axis lifts upwards, right? So he actually printed a full-size elephant by essentially removing the Z limitation and just making the Z-axis rail super long. So he just kept printing it, but it's printing it upside down, right? And then of course the X and Y still remains limited. So he printed essentially columns of this elephant, and he boop, squished it together and made a full-size elephant out of it. But I'm sure that actually took like months to print.
Awesome.
Yeah.
There is one that's actually printed in 3D house.
Right. So those are more industrial grade printers. All right. I think I've used up all my time.
Well, that's good. Thank you very much. All right. Who's up? Would you like to go, Jerome?
And carve it.
Okay, one moment while we set up here.
You're gonna need lights.
I whittled wood and
Well, I've done the presentation first, and then the demo at the end.
Okay.
So I guess we could, no, turn on the light and then.
Okay.
Oh, pop.
Okay.
this all.
It's
Very few times actually solid.
So, do you think,
Okay, so next up will be Jerome Lecomte, a lazy JavaScript developer's guide to Arduino.
Hi everybody, my name is Jerome. I'm a lazy web developer at Avianna, and this is my foray into Arduino. So as Jeff explained earlier, Arduino is awesome. That's my ticket for hardware hacks in the Internet of Things, wearable computing, bots. That's awesome. The only one drawback with it is that the way Arduino works is you upload your program in it, and you program this in a C language. And being a lazy web developer, there's only one language I need to know about. I'm sorry, David, it's not real. It's JavaScript, right? Yes. I'm getting it's awesome. Yeah, so in JavaScript, it's in every browser. It's also on the server side now with Node.js. Pretty much it's like, oh, Java, better, they fixed all the problems, they put script at the end, it works. So how do I use that, which I'm very comfortable with writing all my website and stuff with Arduino? Well, there's a framework called Johnny 5, and it's going to come in very handy. It's pretty much a library that emulates all the Arduino API in JavaScript, and I found a stack that's pretty useful. where Johnny 5 fits really well in it. So here you got your Arduino board, and because the memory is very limited, you're not going to run the JavaScript program there. You're going to flash it with a program that's called the Fermata, that implements the Fermata protocol. So without really getting into the detail of that, you can think of it as a proxy. It's a command protocol, meaning that it listens for command on the USB port. So think of it as a proxy. Every time you tell it to do something, it will pass the command back to the board and then enable the pin or read a value. And something happens on the pins, it's going to send that information back up on the USB port. So then on your server side, you're going to run an Node.js program using the Johnny 5 library that will be the interface layer to your board. So I'll program a JavaScript using all the concepts. You'll have access to buttons, to relays, all the components that you normally plug into an Arduino board. And so that gives me command line capabilities. But if you couple this with another library that's actually multilingual, but that's called Socket.io, and it provides WebSockets. It means now I can tie the Node.js command line process to a web page using WebSocket in between. And then I've got the full HTML, DOM, JavaScript, CSS libraries to build whatever I want and control or command the Arduino board with it. So you notice that in this scenario, the Arduino board is tethered to my laptop or to the server, which if you're building bots or stuff like this, you're going to be limited in range. But there is a way to address this shortcoming with Johnny 5 that I'll mention at the end of the presentation. So a concrete project. Here at Avianna, we had a project that was not very successful. I was targeting pro traders. And I said, well, it's because we focused on wrong personality. So Jeff Ashley and me, we designed Bro Trader. And it's pretty much like an interface that lets bros place trades on our platform by exchanging combinations of high five, fist bump, and elbow bump, or mix of everything. So you got Ashley and Jeff testing the system that was built. The Arduino board that's running the whole thing. The laptop where the program is running, and behind there was some web page showing stuff. Okay, so really, it was very impressive and well received. But the thing is, the core of it used really one thing from Johnny 5 is so actually I got a sleeve there, and maybe I can show this to the webcam. So it's something very nice, very trendy, I think, with one finger, arm that you put there, and you got one switch here, one switch there, one switch there. Like, really, we're talking about 6 switches. Then I click, and it's just a game of matching which ones are being triggered at a time. So one there, and one there. And so we're really talking about the buttons. And if you go to the Johnny 5 website, which is really well done, they've got a very nice API, they've got examples for everything. So that's the you've got a diagram for the example. So this is the button, how to wire it to your board, and then this is the code. So really, you a la Node.js, you include the Johnny 5 library, you create the board. When the board has been created, you get a callback. In this callback, you create a button. Whoops. You tell it on to which pin it's connected on the board, and this is it. When the button is clicked, you got an event that fires, and you get a callback to do whatever you want. And when it's released, you got another callback. And really, I should have been using this button there. Right there. So like power goes into the switch. On this pin, you're reading whether it's open or not, and you've got a resistor. Don't explain to me exactly the role of the resistor, but because I'm lazy, I forget this. So it's a pull down resistor, pull up. Pretty much when the button is not clicked, make sure that the value here is like 0, indivisible 0, whereas when there's an error that goes there, and the button is pressed, it's a 1. But being lazy, I didn't want to even put a resistor on the breadboard, so I used the other one, pull up, which means the board has an internal resistance that you can use for exactly that purpose. So you just plug your ground and the pin you want to read the information on directly to there, and then to mention that a button is a pull-up, you just pass that. Very lazy, very efficient, not a lot of code, not a lot of hardware. Okay, so back there. Okay, so pretty much this is all I need 6 times to read signals from some of the sleeves. And then on the WebSocket side, to make the connection between my server and the web page where I'm going to show stuff, get started docs. Right. It's about this. Again, you require the socket IO library. You pass it a port on which the WebSocket is going to be open on. Then you got this object there. Whenever a web page connects to it, you've got a callback and a socket to that connection, and you can emit messages and pass some data. It's two-way, but for the purpose of like hack, I just needed the board to send, well, the server to send information to the page and not go the other direction. And on the client side, you do this. We include the socket IO library. Again, you connect to local hosts. So in the example, the server was often on port 80. But if you use a different port, you would put it there. You get a socket, and then when you receive a message from the server, so if the server emits news, then you get a news event, and you've got to call back with the data that's attached to it. Really, like both the 25 and the socket library, like literally copied those code examples, put it in my program, and the software part was done. So now on the hardware part, this book, Wearable Computing by Kate Hartman, was very great. I mean, hardware, I've got everything about electronics since my college course. So it contains a very like one-on-one, what is current, how it flows, voltages, intensity, all those things. A couple of chapters to get up to speed on that. Because it's really meant for designers more than developers. And then she goes a lot about wearable projects. So this is like an LED fashion design that you can wear. And she has a couple of examples around another type of Arduino board, because this one is really sharp angle. So usually in wearable design, you use a lead pad board, which is round, and it's really meant for stitching things. But the great thing for me here is that there's a recipe for sub switches, which are, again, those nice orange things on the sleeve there. I could have used pressure sensors, but they're a bit more expensive. So for a hack, I really felt like I needed to have $0 budget. So you get pretty much conductive tape, conductive fabric and felt. So you're going to sandwich a piece of felt with a hole inside between two layers of conductive material, and the hole is going to, that is going to isolate them when the switch is not pressed, and when you press on it, through the hole, the two surfaces are going to connect and let you current. One life lesson I've learned about this, bigger is better, does not apply to sub switches. Really, I don't know why, I felt like it was very important that the switch covered the entire width of my fist, but really, whether this much surface or that much surface connects, like a big surface is just a tiny point connects, the currents will go through. So you'll actually notice that a smaller switch actually works better. And also, the second thing is, I thought it was very important to have a huge hole in between, so that more surface that connects. But that actually leads to a lot of false contact where, as I move the sleeve around, the felt moves a bit and connects, whereas where I didn't want it to connect. So the book had the recipe for that. Manufactured 6 of them. Actually, helped me with the hand stitching. And then what's next? Well, I kind of guessed that I needed to have like wires from those things to the board, and I didn't really feel like soldering the wires to the fabric, so I used a glue gun, which also is not always nice. Which sometimes the glue would go in between the fabric and the wire and not make contact. So the voltmeter was very useful to make sure I have connectivity. And again, the recipe for the sleeve, I just got a sleeve and like, well, glue the things on because I had nothing else available. And in the end, like really, the key was testing step by step to see if like anything was working. And then that's a halfway through project where as I'm tapping the switches, the board sends the fact that like pin number 1, 2, or 3, depending on which switch was being clicked on, and then you'll see the right state was not connected, so the right pins would say not available, but the left ones stay up at the beginning. When I press on them, you can play it again. You can see that like some stuff is changing in my web page, and I was like, this is great, digital and the hardware work combined, awesome. And you notice the middle ones are again finicky, you have to press it both ones, so it's very it works sometimes, it doesn't. Okay, and now I guess it's demo time. So I made a slightly simpler version of that. And just to reiterate a bit about the code, the server part is, again, including socket I/O, opening the port. When a web page connects, I start a puzzle. So the game, it's a simplified version. The game is like find a secret handshake. So the board is going to say, okay, on the left side it's going to be the hand or the palm. On the right side it's going to be the elbow. But it's keeping that for itself, and we have to figure out. We have to guess it by trial and error. So again, once the puzzle is initialized, I'll create a 25 board. When the board is ready, I'll have 2 LEDs on the board telling me if, when things are pressed, if it's the right combination or not. Red if it's wrong, green if it's right. For all the pins, so 2 to 4 is the left hand, 5 to 7 is the right hand. I'm creating buttons called pull-ups. And when it's down, I'm just recording that, hey, that part of the pin just went pressed. I'm checking if the pin I've pressed is either the left combination or the right combination, and that would mean it's a match. And the web page will show either the corresponding icon either in red or in green. And if both like the left and right solutions are pressed at the same time, then it means this problem is solved. So once that has been determined, I'm sending to the web page with socket I/O the fact that the button has been pressed, and I'm indicating which pin it's been and if it's a match or not for that pin. And if the problem is solved, I'm changing the color of the LED. I'm switching the green one on and the red one off, and resetting the puzzle in 3 seconds. Same thing when the button is depressed, record the state, emit to the web page that particular pin has been depressed, and I switch red on because that's probably a safe guess, and green off. And on the website, got a couple of different diffs showing nice pictures. You'll see that designed by Jeff. They're each corresponding to a particular pin. All those pictures are hidden by default. And when we go into the code, I'm creating a socket to the server. When I receive a message that one of the pins has been pressed, I will locate the corresponding image. I will have the active class, which will show the image. And if it's a match, meaning the one I press is one part of the secret handshake, I'll add the hit class, which will color it in green, or the miss class, which will color it in red. And if when the button is depressed, I'm removing all classes, so the image is going to disappear. Okay, see if it works. Live demonstration. So that's starting the board. Then I need to start the content part. Okay, on the server side, there should be another step. Wonderful. Okay, so I'm going to need a volunteer. I'm going to designate Justin. Yep. Let's see. Yeah, also another thing, as I was developing the project, I kept forgetting which pin the switches were connected to, so I actually wrote the number on it. And also there's a left arm and a right arm, so it pays to actually spell it out. So this is the right arm, and it goes on your right side. So you go with this. I've made a nice hole here. There you go. So, sorry. We're kind of limited by the range of wires. Okay.
We're gonna make some trades.
No, we just get the sequence. Okay, so we're gonna try randomly. High five. Okay, so as you can see, that was not bad. And I'm not doing any buffering, so as soon as there's contact, there's a signal being sent. Okay, so red, it's not that. Let's try fist bump. Okay, so one of us is Philippe, it's probably me.
There you go.
It's not fist bump. It's fist bump.
It's elbow bump.
There we go. And if I actually look at the server for a second, sorry, it should have picked another puzzle, so they're down for another try. Handshake.
The next jacket.
Yes.
Wasn't this jacket. I wanted it. It's still not that.
Oh, so one of us was right. All right. One of the drawbacks was as I do a fist, I'm actually pressing on the palm, so I've got two signals going on at the same time. So it's probably okay. Okay, so me and the fist bump, but we're going to try to have a
Okay.
fist bump, elbow.
Yeah.
There you go. It's a match.
Punch him hard.
And so on and so on. Thank you. I've got myself a custom hardware interface for my digital world. Okay. Right, so I was saying that in the stack, originally the Arduino board is not running the Node.js program, it's my laptop, so I'm limited by the USB cable that I thought if the board was supposed to be a bot or something, it couldn't go very far. The interesting thing about Johnny 5 is that the board is an abstract contract, the abstract layer, and by default it's an Arduino one, but they have support for all kinds of different boards out there. And you can pass it what they call an I/O plugin, and you can run it on, for example, a Raspberry Pi. Now, a Raspberry Pi is like a tiny computer, so you've got actually an OS running on it, and a JavaScript VM, which means your Node.js program can actually run this on your board, and now you're not limited anymore by wires, so you could have a bot that runs off the Raspberry Pi board. And so I would have liked to show you the example there. I didn't get a chance to try it, but pretty much I would take the same program, just when I create my board, instead, before I was not passing anything, now I would actually pass an I/O parameter with this thing, Rasp.io, which is the plugin for Raspberry Pi, and everything would be the same except maybe the pins. So Arduino is 1, 2, 3, 4, 5. Raspberry has like 3 different schemes of naming the pins. But again, if you put this into like a config, maybe saying, oh, depending on the time of board I'm running this thing on, I will load the proper names for proper pin names for the board. You would have pretty much like one program that you can run on any type of board. Again, Java runs runs everywhere. So what's next? Another thing I didn't get into, but that looked very interesting, was Silent.js. So Johnny 5 is very low level. It's exactly the same like API and concept you got from the Arduino board exposed in JavaScript. Silent.js seems to be one layer above and is really meant for like controlling blocks and whatnot. Not sure exactly what that means, but I'm assuming you program like higher level things like go right, turn left, and that the framework would kind of abstract that out for you. And another thing I'm going to try to do as a side project is now a candy dispenser. So my idea is to have a candy box, a candy jar that's closed, and like have nice closed eyes and not pretend to the kids that the candy jar is sleeping. But if you can startle the jar by screaming their head off at it, the microphone will pick up the level, and if you scream loud enough, it will actually open the lid of the jar as if, like, oh, you just woke me up. And then the kids can pillage the candies until the lid slowly closes back. So I think that'll be the next project as a try. I've got to find that after that. That's all I've got. Again, JavaScript, which is not meant to be used for Arduino, but you can still do it. That's awesome.
Thank you. So, can you reproduce a Nintendo Power Glove?
Ah, it's interesting. Probably. I would do
with
probably
felt and Arduino.
In its failure, or it succeeds in its
failure? Yes, I could do that.
Probably better off using the physical glove and taking the signals.
Yeah. That's like, well, I guess I kind of recall just that it had like buttons on top, but was it also? I didn't have a glove when I was a kid, but was it like measuring how you would flex your fingers?
It never worked well.
Okay.
I don't think it was as much of anything.
It had a gyro sensor, so
Gyro.
your arm around it and stuff, but not.
Well, and you would an accelerometer on
There was you could steer things by rotating.
Yeah.
So.
You also even have like there's sensors that measure how bent things are, so you can put some line a glove with it inside and tell what you get an analog sensor reading of how flex your fingers are. Yeah, sky's the limit. Just glue, more glue. Cool, thank you.
Thank you very much, Jerome. We have 2 little talks left. Are we going Doug or are we going Richard?
Let me go first. Okay, yeah. I'm going to turn the light off. First.
Okay.
The first thing I want to show is just that there's been a lot of talk about Arduinos, and one thing I did was build down first my own Arduino board. It's just that an Arduino board usually costs like $30. Usually costs like $30 or so, right? So in this case, I just use my regular Arduino board as a programmer, program the stuff on it, take the chip out, and fire it into here, right? And this is maybe like $5 a part. And if you want, you can see my horrible soldering jobs here. It's missing a lot of the extra features you get, like for example, the built-in pull-up resistors. Jerome was talking about things. But yeah, if you can hear this, all it is doing is beeping my amateur radio call sign, and you can slow it up, speed it down based on this potentiometer. And that's basically what I was trying to say. You don't have to spend $30 for every Arduino project you make. You can just use the Arduino as a programmer, take the chip out, and fire it into your own little board. Well, yeah. Yeah. So the other thing I want to talk about is this gizmo I got just recently called the Hacker F1. It's a really neat device. Essentially, it's kind of like a sound card except for radio waves, right? So, but instead of sampling air pressure, it samples radio waves, samples voltage, and it ranges from 1 megahertz roughly to about 6 gigahertz, and it can do up to about 20 megahertz of bandwidth. It has 4 different ports. 2 of these are clock in and out. So ignore those now. Those are for synchronizing multiple ones. And then it has a USB port to connect to your computer. And then it has the antenna port, which is just an SMA connector. So you can use most standard microwave antennas. So it comes with USB cable and this simple telescopic antenna. So I'm just going to screw this in and then extend the antenna just a little bit. And yeah, so I'll probably do the rest with onto the projector there. Okay. Where's this?
Do you need the lighter? Can I get it?
Yeah, I think you can kill it. Yeah.
So I can see it. Yeah. Just those two. Get the slides over.
Yeah. So there's actually not really slides. It's just yeah. So yeah. Basically, yeah. So it comes with some cool command line utilities. The first one is just hackref info. It says I don't have a hackref available right now, so I'm just going to plug one in. Plug it in here actually, and then plug the USB port in. And you probably can't see it in most places, but little lights have come on and they indicate stuff. So there you go. So hackref board is found, right? The first thing I like to show with it is this really cool program called GQRX, and it's kind of like a receiver, like for a radio receiver. So right now, it's looking at the commercial FM band, right? So you can in fact see every single one of those different displays in the waterfall is actually a commercial FM station. So if I over there, yeah, if you listen, you'll hear, you know, that's 96.3. And here's some whatever, So and at this point, actually, I'm only looking at, yeah, I believe 8 megahertz of the spectrum. I can actually do up to 20. If my computer's a little bit faster, I'd show you more, but actually this program maxes out about, I can probably get 10 million samples per second. But yeah, so really, really flexible. And it's awesome for amateur radio because you can look at everyone's conversation at once and figure out who's got the best signal and whatnot, right? So yeah, so the next thing I want to demo, or I want to show really quick here, is David over there was kind enough to lend me these remote control cars, and I just wanted to see what I could do with them, right? And it's very, very simple. Just you charge it up with this. It charges a little capacitor in there, and then when you press the buttons here, it drives forward or backwards, whatever, right? So I just wanted to show you what the process I did to make use of these. So the first, a really cool program is called GNU Radio, and it comes with this sort of editor thing, kind of like Simulink for MATLAB if you ever use that, and it's kind of like a friendly user interface to plugging up radio stuff. So yeah, here's it's kind of like you drag little components. It's a little bit tough to see. I don't have time to go into everything, but I'll just show you this simple one. Basically, what it is this is called an Osmocom source, and it's actually taking complex samples from the hackref itself, and then splitting it off and feeding it into two different windows here, WX-GUI scope and WX-GUI FFT. And they're synced so that the RF flows to them. So basically, if I hit play here, what it's going to do is it's going to open the hackref and start getting samples from it, and then it'll open it. These are actually time and frequency domain displays of the current RF spectrum. So, and I also added a slider here. You can actually see that in here. That's that little thing down here, and that controls the where it's centered. So what I'm going to do is I'm going to press up on this display on this controller board right now. The little car controller. So as you see, there's some big spikes up there, right? Somewhere around here, right? Around 400 and some kilohertz above the center frequency, right? And what I can do is I can take it and take the slider and drag it further up or drag it closer down. And depending on where it's going, it's gonna So I'm gonna leave it centered somewhere around here, right? And by the way, you see that spike in the middle? That's just a DC offset. You can ignore that. Right. So as you can see, frequency domain is really easy there. It's doing stuff. It's just a lot of energy right at that frequency, right? Whereas the time domain, the top one, is a little bit more complex. It's like some waves are going on some of the time. So what I'm going to do is I'm going to turn off auto ranging so I can actually play with these parameters a bit. And I'm going to change the seconds per division, counts per division, change that, with sort of the hope that I can get something I can actually see here. Oops, what am I looking at? So yeah, I'm looking at, see at the bottom there is milliseconds.
Does this come with the hack RF device, or do you
So-
download it separately?
Yeah, you download it separately. So this program, GNU Radio, actually works with a whole bunch of different types of software radios, not just the Hacker app. So it's actually really flexible. So this is basically what I did. So this is a little bit easier to see here. I've just paused it so you can kind of take a look. But the way this protocol kind of works is you see these 4 big long pulses in the middle. It sends those 4 big long pulses, and then it sends a whole bunch of little short pulses, and that determines the command. So here I was holding the up button, so you can see this is the start of one. So you see 4 long pulses, right? And if I hold my mouse over, I get the time. Each one of these are about 1.5 milliseconds long, roughly. And each of these short ones are about 0.5 milliseconds long, and there's a 0.5 millisecond gap in the middle between them, right? The protocol is really just really simple, right? All it is long pulses and then little short pulses. And if I was holding down the down button, it would be a different number of short pulses. So basically, I did this for every combination. Up is this many, counted them out. Down is this many. The combination of holding up and then left is this many, and so on. And I wrote it all down. And then I essentially reversed engineered the protocol. So yeah, I just want to talk just a little bit quickly about what this is. So really, you can think about this as just being a constant sine wave that's being interrupted, right? It's this constant, continuous wave signal that's just being turned on and off, kind of like Morse code keying, right? Another way to actually think about this is that this is actually equivalent to amplitude modulation, except the signal you're doing amplitude modulation for is not actually a voice signal or music or something like that. It's actually a binary square wave signal, right? So the amplitude is either going from full or to low, right? So that's really nice because you can think about this exactly like an amplitude modulated signal. And HackerF lets you do any kind of modulation. You can do frequency modulation as well. You can do phase modulation. In fact, those are 2 of the same things, right? Frequency is just the derivative of phase. But anyway, GNU Radio is really cool. You can explore all this stuff. And I'm just going to stop this right now. And then on the right here, there's like zillions of other little blocks you can put in, and you can drag on your Hilbert transforms and your your low pass filters and any kind of signaling. Digital signal processing stuff you want to do. However, I didn't really want to do that for my remote control car stuff. I actually wanted to do something in Perl. So this is going to probably be the only Perl you're going to see tonight. So I wrote this really simple program that's actually going to use some of my libraries. So I wrote this library called Radio Hacker F, not on CPAN yet, but you can get it on my GitHub page. And then this other one is Valence, which is like a kind of GUI toolkit I wrote also that is on CPAN. So yeah, the first thing I'm going to do is use PDL. That's the Perl data language. Really, really powerful, flexible tool. It's also kind of like MATLAB. It lets you do like operations on large amounts of data without you doing the loop in Perl. It's all implemented in C underneath. And then next, I just have some constants here that basically my sample rate is about 8 million. And the frequency offset is about 470 kilohertz, right? Remember that was roughly the default when I was at 35 megahertz. By the way, the little RC car has a sticker on it that says 35 megahertz. That's how I knew where to go to get 35, right? But if I didn't know that, I could look at this device on the FCC list, which has all the information on the website, or I could just plug in my frequency counter and count the frequency that way. And then, yeah, so there's some scaling and the pulse width. Remember I said it was half a millisecond roughly. And then, yeah, DC offset is just me emulating what I received. So here's my little decoder thing, right? Like I've actually got, this is my little file I had. That's maybe not all of them. But anyway, yeah, that was my original notes. And then, yeah, basically refined it, put it into here and all the combinations in this map. So that this is, the number of short pulses in between those 4 long pulses, right? And then next I have this sub called generate the base sequence. And this is just, me generating like a little short pulse of RF data that I can send repeatedly to cause it to do the command I'm interested in. So it accepts the number of pulses, right? So 10 for up, for example. And the next thing, it just creates this message with just a list of ones and zeros. And there's the 4 long pulses is 1 1 1 0 4 times, and then 1 0 repeated the number of pulse times, right? So it's this list. And then the RLD function in PDL is run length decoder function. So basically, it's going to say for every one of those ones or zeros, expand that a certain number of times, right? Turn the 1 into n ones and turn the 0 into n zeros, right? So that actually turns it to be long enough so that I've got it expanded so that it's the right frequency. And of course, that depends on the pulse width and sample rate, which is why I'm multiplying it there. And then, so the next, the most complicated part to understanding software-defined radio, actually, at least to me, is understanding the concept of complex baseband, right? So a sound card is kind of, if you think about it, the frequency, it can handle the frequencies of approximately 0 up to about 20 kilohertz, 40 kilohertz, whatever, depending on your sampling rate, right? That's called a baseband signal because it handles, signals that start at approximately 0 and go up to some cutoff level, right? The HackRF is actually not a baseband not a baseband sampler. It's a passband sampler because it can't go all the way down to 0. It actually samples at a higher rate, right? It samples, like, for example, 35 megahertz to 47 megahertz, or whatever, right? So you have to kind of shift it down, right? You have to shift it down to the baseband. And when you do that, the usual transform is to do it into complex numbers. And the reasons for that are that it's really easy it's a lot easier to process it for a lot of reasons. But I don't really have a lot of time to go into that right now. But anyway, you can see how I'm constructing a complex number sequence here. I'm saying cosine of my sample sequence is just the thing I developed here, which is just a really long list of like 1, 2, 3, 4, 5, 6, 7, 8, et cetera, et cetera. Just taking the cosine of that. It's turned into radians, by the way, too. But, and then I'm also taking the I times the sine of that same thing, right? And those are called the in phase and the quadrature phase, respectively. But anyway, the point is I end up with this complex series of numbers. And then the next final thing I do is the amplitude modulation. This carrier times equal amps, this is the amplitude. This is the amplitude modulation. I multiply the signal on the carrier. So remember, the signal is just those 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, etc. That's kind of the thing that I'm trying to transmit, the message. And the carrier is actually the sine wave that I developed. So multiplying them together, it's exactly as if you'd plug the signals into a diode and got the nonlinear amplitude modulation combination as if you'd in the analog world, right? And then I just add some DC offsets, not important. And then I take that big long thing, I turn it into bytes because it was doubles before for processing precision, and then I flatten it so it's no longer complex numbers. It's actually just alternating I, Q, I, Q, I, Q. Those are the in-phase and quadrature samples. And the next thing is, now that I've got that utility function defined, all I have to do is open up my HackRF, which is this library I wrote, and then it takes some parameters, like, for example, the frequency and the sample rate, and whether I want to not enable the radio frequency amplifier inside the HackRF. And then the next is I just have some command variables and so on. And next I'm going to install this transmitter callback, right? And this is this callback that I install with the TX, the TX method of the HackRF. This callback will get called a certain number of times per second, right? Like, depending on your sample rate. With 8 megahertz, it's called, like, I don't know, 10, 20 times per second or something like that, right? So it has to be relatively fast. So if the command is in the empty string, which is the default, I'm just going to send a bunch of zeros, right? So I do basically the same thing, take a bunch of zeros, flatten them out of complex, and turn them into bytes in return, right? However, the interesting thing is if the command was not empty string and there's no signal installed yet, I generate the signal, right? So I install that with my generate base sequence method that we defined above. And of course, it takes the pulses that are required from the command, which is the number of pulses. And then now here's where the kind of interesting thing is, right? So now I have this command that say it's 1 million samples long, right? And I need to return a chunk of it, the amount that's needed, the block size that's requested, right? What I can do is use the PDL slice command, right? Slice method, right? So PDL has this really neat read, evaluate, print loop called this PDL command. And yeah, so you can say like PDL, or like you can say sequence 10, right? And oh, by the way, you have to print it. So that's the numbers, 0 through 9, right? And you can say slice whatever I did over here, 0 to 3, right? And that just takes a slice. It returns a new pill. And actually, that actually shares memory, so it's quite efficient. So then I take that and I put it into transmission and I return it, right? However, the next time I want to make sure that I'm in the same location of that slice, right? So what I do is I take this rotate and I say, so say my sequence is this. I go rotate by -3, boom, and then you see how. Well, actually, sorry, it should be forward. So yeah. You can see that now I've appended those 0, 1, 2, 3s to the very end. So the next time it runs, I'm going to give it the next ones in sequence, right? So it's just constantly rotating this big array. And it's doing it in a very efficient way because it's PDL. It's actually not copying the number every time. And then the last thing I do is just use my little valence command line GUI, or GUI toolkit, which is basically just an embedded Chromium from the Atom and Electron projects, right? Like if you build the Atom editor. And then I create a window, and then I do some basic callback stuff. And by the way, I'm going to load this file. And then here's the important thing. I install a listener for an update_cmd event. And when I get that, I actually install the my command into that CMD global variable. And then I reset the signal to undef, so it will get generated the next time the callback is run. Right, so now the simple thing I can do. Well, let me just show you really quick the HTML. So it's just some random styles, some HTML, whatever. And then here I'm using the JavaScript side of Valence, right? I've just got some variables and then function that's called whenever I press it. As you can see, really simple JavaScript and HTML here. So now I'm just gonna go Perl, blah 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 blah. So yeah, as you can see, this is the exciting window that's open, and it says you can't see that, but it says press the arrow keys. Right? So if I press up, it's going to show that. If I press left, it's going to show that. Right, down. Right? So now, let's see if this actually works. I'm going to take the little car. You didn't try it. And charge it. Because it needs to charge a little bit. Okay, that should be good. So I press up and down.
That little light is a car.
So yeah.
It's impossible without JavaScript.
That's the grand finale is driving the little car with the arrow keys. But trust me, there's so much more you can do with software-defined radio. As an amateur radio operator myself, I'm really excited for the communication potential. And I just want to plug the Toronto Amateur Radio Club. I'm going to give a more comprehensive talk about this probably after the summer at some point. But yeah, HackerF1 costs about $350, so it's not ridiculously expensive, but it's not extremely cheap either, right? So yeah, thank you very much for listening. And anyone who's got questions, I'll try and answer them.
You consider HackerF the best SDR that's out there right now?
I'm sorry?
Do you consider HackerF the best SDR?
Oh, absolutely not. No, there's much better ones.
Okay, the most cost-effective one.
Yes, the most cost-effective for sure. Yeah. So one of the disadvantages of the HackerF is that it's not a full duplex device, right? It can only receive at one time or transmit. It can't do both simultaneously, right? There are some that are in fact full duplex. Another disadvantage of the HackerF is that it's only got 8-bit samples, right? 8-bit complex samples, so you have 2 bytes, right? Whereas there's some that are 16 or even 24 if you start getting it, or even 32, some of the professional Texans from DSPs and so on. And then also there's ones that can do a lot more bandwidth, right? 20 megahertz is quite a bit. However, there's some protocols, like for example 802.11n, that need even larger bandwidth than 20 megahertz. But yeah, for just experimenting and playing around, HackerF is just, I really like. Everything is open source, even the hardware design, everything. It's really neat device.
What's the range of the signals you can send?
Good question. So that depends on a lot of things, obviously, right? One of them is that the HackerF's power capability is not identical over its entire spectrum. It's especially good around the 2.4 gigahertz range, because that's kind of the middle of its band. So it'll do go further that way. Also, it depends on the antenna you use, of course. With anything radio, antenna is really critical. This one is kind of, it's not ideal for the 35 megahertz that I'm using here at all, right? This is because it's telescopic. It's good for most micro, UHF into microwave range. It would be good for. So yeah, this is really designed for like the few gigahertz, low gigahertz range with this antenna. But if you get better antennas, like for example my HF antenna, plug that in, like it's a really big one. I can listen to like the 20 and 40 meter band, like you'll see Richard talk about here in a minute, and it worked great, right? The other thing it depends on is the actual signal you feed into it, how amplified that is, and also the different amplifier settings you have in here, right? There's multiple different amplifiers. There's the final stage RF amplifier, there's the intermediate frequency amplifier, and then there's another amplifier for receiving too. So all that being said, you can put out hundreds of milliamp or milliwatt of power. So line of sight you can go for miles and miles and miles, right? In a building kind of situation, like for example, this will put out substantially more than your Wi-Fi card will. So take that, like probably several times more than your Wi-Fi card, right? So the range is, compared to like your average Bluetooth Wi-Fi sort of peripheral, very good, right? But compared to like this thing that Richard's going to show you, it's not good.
So can you take control of Jerome's Cylon candy machine?
Oh, I might be able to. We'll see. Yeah.
So you mentioned at the beginning there's a way to connect multiple of these things together?
Yes.
So what does that look like to the interface? When you plug it into your computer, does it register them differently? Do they all funnel through the...
So yeah, so the question is what happens when you have multiple HackerFs, right? I've never done it because I only have one HackerF, but the HackerF info command looks like it'll print out a list of them, and then you give you the device IDs, like the serials for each one, and then the libraries, the little libraries accept the serial number, so you can choose which one to control in that case, right?
Right. What about like that GUI that you're showing me you can actually see?
Yeah, so I mean, I haven't put this support into the Perl bindings yet, but eventually, if I do get another HackerF, I'll make it so it accepts the device info, and then it would be up to me to code how I want to do it, right? Like maybe I'd want, two different, completely separate keypads, one you drive with WASD and one, right? Like,
sorry, not that GUI, the
GNU Radio.
Oh, GNU Radio, yeah. Very good question. Yeah, I think you would just get two Osmocom sources, and you can do whatever you want with them. Yeah, so the really another neat feature is those two ports that I basically glossed over initially, called the clock ports. When you get two HackerFs, you can get an SMA cable that connects from one clock in to the other clock out, and they'll basically like partner, and they'll make their frequencies lock and their phase lock. So the really nice thing about that is that all of your samples will be in phase relative to the time, and all the frequencies will be exactly precise too, right? Like, well, they'll be relatively precise, right? So when you're using them in tandem like that, it gives you a lot. Like they're both stable to the same extent. And actually, just to mention another really cool program with this is, because this has like it's not perfectly exact, the frequency is. It's pretty good. But there's this one program called Calibrate, which actually you run the program, and it looks for all the different GSM signals around you, and it knows roughly what frequencies they operate on, and those are usually very stable, good, accurate signals, right? So it uses those to calibrate itself to be the correct frequencies.
I have a practical problem which I think this might address, but let's take it offline afterwards.
Sure, yeah, of course, yeah.
You want us to hack a cheat.
Yes.
Thanks very much.
Thanks very much, Brett. For the record, Mr. Hoyte's idea of a very simple program is what most people would think of as Damien Conway territory.
Well, it's even if it's parent, I didn't get it.
Where did you get it?
No, I got it from Google.
Just working.
It was like, because it's only
Is your internet connection right here? Because
It should be.
I can't reach the my computer. What network are you on?
Probably Avianna.
Oh, that's why.
Oh, yeah, I don't. There's so many computers with Wi-Fi.
Okay. So on my computer. Okay. Come on over.
Sorry, I've got a laptop on Wi-Fi.
Don't touch anything else.
Okay.
The only problem is I can't adjust any of the settings.
Well,
What do you think?
are you on?
All right.
Okay, yeah, I'm on the guest.
Who uses Sure. Sorry, we'll get going in just one second. Avianna. Oh. Okay. So in a moment, let's Richard gets set up. We'll move on to his amateur radio amplifier kit with a whole bunch of letters I don't understand, but it's going to be very impressive. 20-meter QRP amateur radio There we go.
Perfect. All right, so this will be pretty quick, simple presentation. So basically, I have on the table here, I have a QRP radio, which I will explain.
You can bring it in front of the camera if you like.
So
What are you standing for?
So it's I'll explain in a second, but I won't really explain because it's amateur. What's QRP? So QRP rigs such as this FT817 basically is a low power transceiver. So QRP basically generally means low power. What that means typically is 0.5 to 5 watts of transmission power. So Doug was just talking about his HackRF putting out a few hundred milliwatts. So this will be like 500 to 5,000 milliwatts of output power. A typical radio transceiver, however, that you normally would have an amateur radio that you connect up to wall socket will put out anywhere between 50 to 100 watts, and sometimes up to 1,000 watts, depending on if you have a properly licensed for it. So QRP is basically like low power radio that people kind of do for the fact that it doesn't use very much power. This is very small, portable, and battery powered, as well as just for the challenge of it. The harder it is, it's harder when you have less power. So, but even then with a low power, with a good antenna and good environmental conditions, you could make with this radio running on batteries, you could make digital and CW Morse code contacts around the world. Reach New Zealand with this conditions for right. So, however, sometimes it is nice to have more power. So you go and you buy your fancy QRP rig, and you're like, well, I want a little bit more juice sometimes. This comes in handy if the band conditions are busy, so you have a lot of chit-chat and so on. It's very hard to be heard sometimes over the more stronger signals. You can have noisy band conditions from atmospheric conditions, solar storms, that kind of thing. And just in general, go further, especially with voice, because of the rare bandwidth that's required for voice contacts. You need more power to be able to be heard. So I purchased this kit from Ramsey Electronics. It's an amplifier kit, and it's specifically designed for a particular band, the 20-meter HF band. So I'll open it up here.
So, which is about 14 megahertz. Yeah, so you get this kit, which I put together myself. So it comes, they give you all the parts and everything in the instruction manual. And the idea of this kit is that it will, so it's designed specifically for the 20 meter band. It will run off a 12 volt DC source. So that could be a battery, or you can plug it into an adapter that's in the wall. And approximately will amplify the input signal to about 20 plus watts. Depends on how much voltage you have in certain conditions. But you can get about 20 watts out of it. So that's pretty substantial because, you know, as I said before, you have radios that are plugged into the wall that's 50 to 100. Getting 20 is actually pretty good. That's only about one S-band lower. Essentially, that means the signal is only about half as strong as a 50 or 100. So it's pretty good to get out there, especially, again, it's relatively small and lightweight. So we'll just go into a quick kind of demonstration or overview of how it does work. There's basically three major operations in this amplifier and in most amplifiers that would be of this type. There's, first of all, a transmit relay, transmit-receive detection relay. So this basically detects when you are on your radio and you say, you click to transmit, it will detect, hey, the person's trying to transmit, and it will switch on this amp. Because normally you don't want this amp running when you're just listening because it's wasting power. So there's a circuit that detects whether or not, if you're transmitting or receiving. There's also in here a class AB amplifier, which is the actual circuit that will make amplify the power. And finally, at the end, there's a low pass filter. So after you've done all of these operations on the signal, there's going to be like a lot of high frequency harmonics, this kind of thing. So you pass it through a low pass filter to kind of smooth those out. So here's kind of, I don't know, you probably won't be able to see it too well, but the circuit diagram of it. So you've got, this is the transmit receive area. This is the amplifier here, and this is the low pass filter. So basically your signal comes in over here, your radio, and comes out here amplified. So normally if you're just not doing anything, you're not transmitting, this switch over here is normally closed. So the signal will just come in, go through, and it will just go straight out. So nothing, it bypasses the entire circuit. And then when you go to transmit, this circuit here will detect that, and what it will do is it will switch this relay here. This is the same relay, it's just K is the relay. So it switches these. So now your signal will go through all this guts. And the first part it will go to is this will amplify, and then it'll go through here and filter, and then the amp go up. So that's kind of the basics of the circuit. And we'll talk about just a little bit more specific details of the individual parts. So the transmit receive detector, the way it works is, so normally it's closed, let's say there's no signal, you're not transmitting. As soon as you start to transmit, you're going to have a signal that's coming in here. And it will come in, this just filters it. You have these diodes here that will basically rectify the signal, which means the signal's going up and down, negative, positive, and this will basically just change it to be a positive portion of it. And this goes through a pair of transistors here. These are bipolar transistors. These will basically just amplify the signal to a point where the sufficient current will be generated by the signal going through that it will then trip this switch here. Right? This is a relay, so what that means is it's magnetically, so normally it's in one position, and if you go current through it, there's a magnet in there that will physically move the switch to open it. So that's how the transmit TR circuit works. There's no power, this will be closed, and as soon as you apply the transmit power, this will open. And the next bit is the actual amplification circuit. So now that your signal is coming through here, what happens is you first go through this center split transformer. And what this does basically is you have your signal again, there's some positives, there's some negatives, say a sine wave. And this will split it into two parts. So the positive part, or who knows which one, but one of these is positive, one of these will be the compared negative part of the signal. And so each part is split, and then it's amplified separately. So you amplify the positive one, and you amplify the negative part of the signal separately. These are using MOSFET, I think they are N-type MOSFETs. And basically this is where the actual amplification will happen. And at the output, you'll now have your amplified positive and your amplified negative signal. And you now need to recombine them, which is what this transformer then does. Over here, again, you bring in your positive negative, and out will come just your combined signal.
This bit up here is just to bias these transistors. So this is like what's known as an AV type amplifier. So class A amplifier is where you basically have just one transistor. It's always running, and you put your positives and your negatives through. It's very power efficient, generally 30% efficient. Another type of transistor setup, amplifier setup you can have is class B, where you have two. You do this where you split positive and the negative, and you have these two. The problem there with that, though, is that there's a little bit of a gap. So you have like one transistor that there's a positive signal, it starts amplifying, and then there'll be the negative one that starts amplifying. But between those two, there'll be kind of a gap where they're both off. So you get a lot of harmonics, a lot of distortion. So one way to solve that is to take these transistors and you bias them with a bit of a positive current or positive voltage all the time. So you give up a little bit of power efficiency, but because you do that, you'll lose the gap will be significantly reduced. So that's what this does, is that this circuit up here is tunable with a variable resistor, and basically this will bias a certain voltage on these guys so that they will always be producing the optimal signal. And then the final bit is pretty straightforward. It's just a standard low-pass filter with a couple coils and capacitors. So, from your basics in electronics, if you remember, capacitors they block low frequency, and coils block high frequency. So the idea here is that as the signal is going through these coils, it is going to be the high frequencies are going to be attenuated, and these coils just basically bleed off, or these capacitors, sorry, just bleed off the direct current part to ground. So essentially, signal will go through here and this will actually attenuate any high frequency harmonics. And then finally, you go out and it's open. So show a quick demo of it in action. So on the table here, I just have a few things that are kind of useful to have for this. So I've got my radio, obviously. And unfortunately, my internal battery died, so I have to use this MacGyvered up this external battery here. All right, so radio's on. And so what I have here is I don't actually have an antenna. I'm not going to actually transmit anything, but I have what's known as a dummy load. So this is what you would use if you were tuning up your antenna. Because what can happen is if you don't have anything connected and you start transmitting, a lot of the radio frequency energy will essentially reflect back into the circuits and can damage your ticket. So I'm going to connect up this. Let's see. So I got my circuit here. So and this here is a power meter that will basically allow me to measure the amount of power that I'm putting in. Any questions, anyway, by the way? Boring to watch some people stuff here.
I assume this will be very handy when the zombie apocalypse comes.
Essentially.
Yeah, just going back to your question about what QRP stands for. It doesn't actually stand for anything. They're called Q codes.
Maybe like QEM.
QEM, maybe.
Yeah, that's a request for this year.
Okay. Yeah, the amateur radio ones are QR and QS are the reserve parts. And yeah, QRP just means low power or reduced power. And yeah, there's QRY, which is switch frequency, and there's QRZ, which is who's calling me. And these are just things that were more convenient to tap out Morse code a long time ago than actually saying, could you please reduce power?
QEM means closest to stage, and QDR is.
Oh, okay, right. So those are aeronautical or yeah. Nice.
All right, so I've set up this the circuit here. So basically, I have the radio. It's outputting at about 20 meters. I've set it to AM because I wanted to send it essentially a carrier wave, full power, and it basically is connected up to the input of the amp. And then the output goes to this power meter. It'll measure the power, and then finally it goes out to the. So right now I have the amp turned. There's a switch on it where you can basically control whether it's on or off. So I have the amp off right now. So I know you won't be able to see it, but you can come up after if you want. So I have a power meter here, and I start transmitting.
Could you perhaps go to the other side, Richard?
Sure.
So I can, no, just like around the other side there so we can see the power meter go.
All right.
Wow.
Kind of space the camera. So it won't move very much. It'll move, so it's at 0 now, and now it's at about a half. So half a watt. You can actually control how much power is putting out. Right now it's set to the lowest power level, so we'll be putting out about 500 kilowatts. Anyways, now I'll turn on the amplifier, and nothing will happen because of the transmit receive circuit. But now, you'll hear it as well. You'll hear the relay close. This is working. Okay, that's right. I forgot to plug in the amp. That's kind of useful. Hopefully those will reach. Yes, you don't get free power, unfortunately. All right. So now you should hear the relay close, and you'll see the power meter move significantly down. So let me change the radios, change the power here.
I think the plug is sideways.
You also whistle into it.
Sorry?
You also whistle into the mic.
Well, it's on AM, right? So. This is probably not the. Anyway, so you can see that the signal compared to, and then I turn this off. So, yeah, it's a simple project that you can get and build. You get to wind your own transformers and your own coils. And yeah, I'm not by any stretch of the imagination electronics expert, but I was able to put this together. And yeah, it's not too difficult, just soldering most of it. Yeah. Any questions?
How hot does it get?
It does get a little hot. You can see here on here, there's actually these. So these here are the two MOSFETs, and these are like, you can see the heat sink that's put around them. So if you're continuously transmitting, these can get pretty warm. I'd say like
25 watts.
Well, yeah, it's 25 watts of heat dissipation, so they can get up to probably 50 or 60 degrees.
How do you test that when you're building it?
Sorry?
How do you test that to make sure that the various parts of the thing are working?
Well, I mean, you can test it by looking at the output that you get here. There is actually some there's a jump point here as well. So one part of it is to bias the circuit properly, so there's a variable resistor here. And there's actually a part in here where you can just connect up a jump point, a probe point, where you can put a voltmeter in there and basically make sure that you're tuned it correctly.
There's not much to tune the power amp. So
this is biasing.
It'll either work or it won't.
Cool. Well, thanks.
All right, well, thank you very much to all the presenters. Richard Farr, Doug Hoyte, Avianna Chao, Jeff Razon, Jerome Lecomte. I think you had the Stravia thing about next month?
Oh yeah, so we're looking at doing a Mojo night, so some talks on Mojalicious, and we just need some volunteers to talk to it. So it doesn't have to be a long talk. We're looking at more of like a sort of beginner, like introduction to Mojo. So.
There's also there's another meetup group that wanted to kind of have a co-meeting, wasn't it?
Yeah, Techalicious.
Yeah. So the Techalicious Toronto group was looking for something. So if anyone has some Mojo knowledge, Justin. That guy right there.
Last talk.
It did.
I mean, you almost haven't heard it.
Yeah. Everything else is like that.
In September will be lightning talks. So,
Ugly guy.
Yeah.
And September, for all, September is often one of our best attended talks of the year. 5-minute tech talks, any subject, not restricted to pro. Show your favorite library, framework, language, maker project. Talks are generally supposed to be 5 minutes is the rule. We're a little lax on that. It can go, 7-8 minutes unless we get really a lot of people. So please, anyone interested, hit any of us up on meetup.com. There's a Toronto Filmmaker mailing list. We'd really like to have you. Really great opportunity for first-time speakers to get some experience talking. And I guess we'll see you next month. Thank you.